Hello everyone, this is Doug, and in this video we're going to talk about naming binary covalent compounds, and we're going to sort of compare and contrast that to how you name ionic compounds. We'll go through a few examples and talk about the rules. So first of all, naming the binary covalent compounds, like what does that mean? Binary just means that there's only two elements. So we're talking about there's only two elements, not two atoms, but two elements. So like boron and chlorine, for example. And by covalent, right, we're talking about those things that have a small or no difference in electronegativity. Right, so the things that are not ionic, they don't have a really large difference in electronegativity. And so an example of a binary compound would be something like, let's say AlCl3, right, because it has two different elements, aluminum and chlorine. We are not talking about something like C2H6O because that has three different elements in it. So we're not talking about things that are like tertiary or they have to have more than just two elements. This is just covalent compounds that only have two elements. That's it. And like I talked about in previous videos, right, these have different, whether it's ionic or covalent, that means you're going to have a different nomenclature system, a different naming system, right? So calcium chloride, I don't need to, we never use multipliers for calcium chloride because I know the charge of calcium and I know the charge of chloride, I know what the formula is. So someone says calcium chloride, you should immediately know what the formula is, right? Because I know that calcium has a +2 charge, right? It's in the second group. It's going to lose 2 electrons to become like the nearest noble gas. And I know chloride is a -1, has a -1 charge because it just needs to gain 1 electron to look like the nearest noble gas to fill its shells. In order for this to be a neutral compound, I know that for every 1 calcium, I must need 2 chlorines so I can balance that out. Now, what's different about covalent compounds like nitrogen oxide is that they're not charged, so I'm not trying to match charges to make a formula. We're not going to get into how these bond. That'll be for a future discussion, but it's more complicated with covalent bonds. There's lots of different ways that something can bond. Like, for example, there are compounds that are like N2O. There's NO. There's NO2. There's NO3. There's N2O5. There's all kinds of versions of mixing just nitrogen and just oxygen. And so to say nitrogen oxide is not very helpful. It's not, I don't want to say ambivalent because there's not two choices. It's just it doesn't point to a specific molecule, right? To say nitrogen oxide. So what we're going to see here is that we have to use multipliers. We're going to need multipliers to say, well, in your nitrogen oxide, how many nitrogens are you talking about? How many oxides, how many oxygen atoms are you talking about? And so we'll use multipliers like mono, which is 1, di, which is 2, tri, which is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, deca is 10. We probably won't see beyond that, but you just keep on going for however high you need to go. And you've heard these multipliers before, even if you've never taken chemistry before. Almost everyone has heard of carbon dioxide. Real big hot topic right now, greenhouse gas, climate change, all that sort of stuff. So carbon dioxide, and you probably know that carbon dioxide is CO2, right? You have a carbon and you have 2 oxygens, carbon dioxide. And that's different, right, than carbon monoxide, which is just a carbon and 1 oxygen, right? Mono meaning 1, di meaning 2. That's how I knew how many oxygens to draw there. So we use these multipliers, but just for the binary covalent compounds. We never use multipliers for the ionic compounds. So that means if I went back up here to these nitrogen oxides, I can actually name these now if I know what the multipliers are, right? I can call this, for example, and we'll do more examples on the next page, but this would be a dinitrogen, right, because there's 2 nitrogens, dinitrogen monoxide, right? Dinitrogen because there's 2 nitrogens, and monoxide because there's 1 oxide. I could skip down to this one right here. I won't do all of them, but this would just be nitrogen. That R got a little away from me there. This would be nitrogen, and then there's 3 oxygens here, so trioxide. And now I have 2 different names for 2 different nitrogen oxide species. So now if I mean, right, if I mean this one right here, I get to call it nitrogen trioxide, and now everyone knows I'm talking about NO3. Or this one up here, if I want to talk about N2O, I just call it dinitrogen monoxide. And again, I won't name all the rest of these, but you can probably figure out them on your own after watching this video. So here's your schematic about how to name the binary compounds, just like I gave you one for naming ionic compounds. The ionic compounds, I think, are actually more complicated, just because you have to deal with the transition metals and because you have polyatomic ions. Naming binary compounds is a little more simple here. So the first atom in a binary compound is always the less electronegative atom. Just like you put the cation first for ionic compounds, you put the less electronegative atom first. The second atom is always the more electronegative atom. For the first atom here, you do use multipliers, right? Like all the ones I showed you on that previous slide, mono, di, etc. But the key thing to know here is that we do not start with mono. Like you don't say monocarbon dioxide, you just say that it's carbon dioxide. So right, we don't use mono for that first atom ever. You just never put mono there. Why? I have no idea. That's what the IUPAC decided. It's a bunch of old white guys in Europe decided. We follow their rules, so that's the rule. And then also you may have noticed on that previous slide, I didn't change the name of that first element at all. If it was carbon, I called it carbon in the name. If it's sulfur, you call it sulfur in the name. You don't change the ending at all. So it's kind of like, again, like cations, like when we did ionic compounds, the first thing's name doesn't change from what it says on the periodic table. Now for the second atom, the more electronegative one, you do use multipliers, and you use them always. If there's only one, you say mono. If there's 7 of them, you say hepta. You use the multipliers for every single second thing, however many there are. But for these, like you probably saw again in the previous slide, and like you did with anions, is you change the ending to "ide." So nitrogen would become nitride, bromine would become bromide, oxygen would become oxide, sulfur would become sulfide. So you change the ending to "ide." So here I have the example of CCl4, which is carbon tetrachloride because there's 4 of them, but instead of, it's not tetrachlorine, it's tetrachloride. So let's look at some examples and apply this. So here's a few. I've actually already named a couple of these. I'm going to do the first couple and then give you time to do the last 2. But what I'm going to do here is I'm just going to look at, well, what's the first atom? In this case, it's carbon. So I know I don't change its name. I just call it carbon. And then I have the second thing, which is the more electronegative thing. I know that that is going to become oxide, right? Oxygen to oxide. And I need to say how many there are. There's 1. There's just 1. What we don't do is we don't keep both those O's. So I don't say monooxide. I don't say monoxide or anything like that. We're going to drop one of these oxygens. And you'll see this written in books and stuff too. But the idea is that we don't say monooxide. We just say monoxide. So we don't put, and this is probably an English language thing, but we don't put 2 vowels right together like that. So carbon monoxide. Let's go to the next one. Same thing. I've got a sulfur in front. Yes, there's only 1, but I don't use mono for that. This is just sulfur. And then if I look at the second thing, it looks like I have oxygens again. So that'd be another oxide. And it looks like there's 2 of them. So I know it's di. So I case sulfur dioxide. And you'll notice that with this one, I didn't drop a vowel. We do say dioxide, but we don't say monooxide. We don't say OO or OA. So I'm going to write this off to the side here. So you don't say OO, you're going to drop one of those and just make it an O. And you don't say OA, you're going to drop that and just say O also. So now at this point, I want to pause and let you take a crack at these last 4. Please go ahead and pause, see what you can do, and we'll come back and do these together real quick. Okay, so hopefully you took a minute to try these here. So just real quick, right, we've got 2 nitrogens, so we've got dinitrogen, because now there's 2 nitrogens, and then we have 4 oxygens, so tetroxide. right? And here's an example where I didn't say tetraoxide, I said tetroxide, which was an example of this. If we go over to here to xenon with 6 fluorines, this would just be xenon. There's only one of them. And then this is 6 is hex, is hexa, so xenon hexafluoride. If I go to water, right, we call this water, but its fancy schmancy name would be dihydrogen monoxide. Dihydrogen monoxide. And then lastly here we have tetraphosphorus. And then I have 3 sulfur, so trisulfide. And I apologize if some of these got squished together. These are 2 separate words. The first thing in blue is one word, then there's a space, then you have the thing in purple. Those are 2 different words here. My xenon hexafluoride got a little close together there. Anyways, that's how you name the binary covalent compounds. That's really it. You got to use multipliers. You don't have to worry. There's no polyatomic ions or anything like that. You don't have to worry about metals being in there, those transition metals, because they're probably not going to form primarily covalent compounds for us at this point. So I have so much practice online for this. So do lots and lots of practice. Make sure this is like the easiest thing ever, because we're just going to use these names for the rest of your chemistry career. We're just going to use these names. So very, very important. So study up. Good luck.